Okay, this video is reviewing a general first-order ordinary differential equation with constant coefficients. This equation will be homogeneous, and we're going to practice the technique for infinite series solution. The equation we're choosing is y prime minus y is equal to 0. And one of the reasons we're choosing that is it has a pretty trivial solution, and as a result we'll be able to see if this technique actually reproduces it. So here we go. The technique involves substituting in the series y equals summation m equals 0 to infinity a n x to the m. So what this will do is produce a series, a polynomial series, basically called a power series. The first term is a naught x to the 0 plus a1x plus a2 x squared plus a3x cubed, and on and on. Now, in order to substitute this into the original differential equation, we'll need it and its derivative. So the derivative would be y prime, and of course that's going to be the summation m equals 1 to infinity. I'll explain the index change in a second. And then we just take the derivative of the definition of the series. That's going to be m a m x to the m minus 1, just using the power rule. This will generate a series that's equal to, well, the first term of the derivative, I know based on the polynomial, isn't going to have an a0, because that's a constant and the derivative of a constant is 0. That's why we raise the index up to 1, because there would be no a0 term in its derivative. In addition, notice what would happen if it was 0. The coefficient of m would make the whole term 0. So there's no sense having that particular term, and that's why we raise the index up. It's really common when you take the derivative of an infinite series to raise the index up to compensate for the fact that you differentiated. Okay, well, let's go ahead and look then at the expanded derivative. There's no a0 term, so the constant term is a1 plus, and I'm going to keep these in columns, the x term is going to be given by 2a2, 2a2x, plus the x squared term is going to be given by 3a3x squared, plus, and while we don't show it up here, we know there's an a4, x to the 4th, so that's going to make 4a4x cubed, and on and on. Okay, now it's time to do the coefficient matching, which involves basically plugging these both in here. That can be really messy, and of course it'll produce a long polynomial, but we can shortcut it a little bit. Our whole purpose for substituting it in is to see if there's relationships between the terms. And I can test that out without having to do the substitution, just term by term. So term by term, let's look at it. a1 and a0 here are the only constants, and I know the form of the equation tells me to take the derivative minus the function, so that's a1 minus a0, a1 minus a0. Those are the only two constants in the entire series, so I know together they're responsible for producing 0 because no other term can help them. So they equal 0, and that means a1 is equal to a0. Let's see if the next term gives us even more relationships. So the only x terms in the entire series is going to be a2, 2a2 and a1, so 2a2 minus a1 equals 0. And from that I get that a2 is equal to 1/2 of a1, but a1 was already equal to a0, so it's 1/2 of a0. And this is encouraging. I'm getting the whole series in terms of a0 alone. That's really one of my goals. Okay, the next term is going to be 3a3 minus a2, and that equals 0, and that produces that a3 has to be 1/3 of a2, but a2 was 1/2 of a0, so when that's substituted in, it's going to make 1/6 of a0. And you can see these denominators are starting to turn into factorials. This is 1 factorial, 2 factorial, 3 factorial, so that pattern's starting to emerge too. Okay, the next term is going to be 4a4 minus a3 equals 0, and that's going to produce a4, which is going to be equal to 1/4 of a3, but a3 was 1/6 of a0, so that means 1/24 of a0. And once again, there's that factorial formula coming out again. That's 4 factorial. So it looks as if every term in this series is in terms of a0 and a factorial of the index. So That's heartening. Now what we can do is go back to our substituted function y, and I can start filling in information for how a0, a1, a2, a3 actually came out as a result of substituting into the differential equation. So I'll do the terms first, and then we'll see if we can come up with a formula that represents it. So first the terms. I know the first term of it was a0, and that exists. The next term of it was a1 times x. Well, a1 is also a0, so it's a0 times x. The next term was a2 times x squared. Well, a2 is 1/2 of a0 times x squared. And then the next term was a3 times x cubed, and a3, of course, is 1/6 of a0 times x cubed, and on and on. The next term is going to be 1/24 of a0 times x to the 4th, and it continues. Well, I can see a pattern that has clearly emerged, and that is that a0's in every term. So this is going to be equal to a0. And then there's an infinite series that remains. Let's do a better symbol than that. The infinite series is m equals 0 to infinity. And then each term's x value is generated as x to the m divided by m factorial. So this term's x is generated that way. X to the 0 is 1. This one's x to the 1 divided by its factorial, 1. This is x squared divided by its factorial, 2 factorial. X cubed divided by its factorial, 3 factorial, and on and on. And the good news is this portion of it right here, that's a Maclaurin series. That's the Maclaurin series for e to the x. So that means our solution is a0 e to the x. Let's see how that compares to the original equation we started with. Y prime minus y equals 0. If we chose to substitute in, using the technique we learned way back in chapter 1, if we chose to substitute in c e to the lambda x, what we're going to find out is that the characteristic equation that comes out of this is lambda minus 1 equals 0. That means lambda is equal to 1, and substituting that back in produces a solution to this differential equation of a constant times e to the x. Notice we get the same solution through the infinite series method that we did through a more traditional approach. Now that doesn't mean this is a good candidate for a series solution. This actually is a pretty bad candidate. If a question like this were on the exam, we certainly wouldn't go through this process to get this differential equation solution. But understanding this technique through a simple example is really valuable, because as the examples get more complicated, we'll still be employing the same technique, and being good at that technique as a result of foresight and seeing where you're going with it is a real advantage for those problems where you won't. The next example we do will be a little bit more complex.